In accordance with the inflation theory, the early universe expanded exponentially quickly for a fraction of a second following the Big Bang. In 1981, cosmologists introduced this concept to address a number of significant cosmological issues. The horizon problem is one of these issues, along with others, but we will discuss these problems that inflation theory need to explain in another video. In physical cosmology, cosmological inflation, or simply inflation, refers to the theory of exponential space expansion in the early universe. It is believed that the inflationary epoch lasted from 10 to the power of minus 36 seconds, to between 10 to the power of minus 33 and 10 to the power of minus 32 seconds after the Big Bang. Welcome back to my channel. Let me explain inflation theory. I will try to address this subject for the general public. We need to see the inflation as a sudden burst. The universe continued to expand after the inflationary period, but at a reduced rate, in fact is still expanding even today. After the universe was already over 7.7 billion years old, 5.4 billion years ago, the acceleration of this expansion due to dark energy began. The inflation theory proved to be successful, but the particle physics mechanism responsible for inflation is unknown. It is like we know gravity, but a quantum theory of it is always out of grasp. The fundamental inflationary paradigm is accepted by the majority of physicists, as a number of inflation model predictions have been confirmed by observation, but there is a significant minority of scientists that disagree. The inflaton field is the hypothetical field believed to cause inflation. In a space that expands exponentially, or nearly exponentially with time, any pair of free-floating objects that are initially at rest will move apart at an accelerating rate if they are not held together by a force. From the perspective of one of these objects, space-time resembles an inverted Schwarzschild black hole. Each object is surrounded by a spherical event horizon. Once the other object has passed this horizon, it can never return, and even light signals it transmits will never reach the first object, so long as space continues to expand exponentially. In the approximation that the expansion is exactly exponential, the horizon remains immobile, and at a constant physical distance. This region of an expanding universe is characterized by the following metric. This exponentially expanding spacetime is known as a de Sitter space, and it requires a cosmological constant, a vacuum energy density that is constant in space and time, and proportional to lambda in the preceding metric, in order to be sustained. For exactly exponential expansion, the vacuum energy has a negative pressure P, equal to its energy density. The equation of state is P equals minus rho. Typically, inflation is not precisely exponential, but rather quasi or near exponential. In such a universe, the horizon will progressively expand over time as the vacuum energy density decreases. Our universe began with an explosion, a Big Bang. The bang stretched the very fabric of space-time, and dispersed superheated matter throughout the universe. As it expanded, the matter cooled and began to aggregate, creating atoms, then elements, then stars, galaxies, and eventually everything we know and observe today, including astronomers that observe the universe as it is. Inflation is a period of supercooled expansion during which the temperature decreases by approximately a factor of 100,000. The precise decrease varies by model, but in the first models it was typically between 10 to the power of 27 Kelvin and 10 to the power of 22 Kelvin. During the inflationary phase, this moderately low temperature was maintained. When inflation ends, the temperature returns to its pre-inflationary level. This is referred to as reheating or thermalization, because the large potential energy of the inflaton field decays into particles, and fills the universe with standard model particles, including electromagnetic radiation, initiating the phase of the universe dominated by radiation. Since the nature of inflation is unknown, this process is still inadequately understood, though it is believed to involve parametric resonance. The Big Bang can be explained in this way, according to MIT physics professor Alan Guth, and his collaborators, Andrei Linde, of Stanford University, and Alexei Starobinsky, of the Landau Institute of Theoretical Physics of the Russian Academy of Sciences. They have been awarded the 2014 Kavli Prize in Astrophysics for their contribution to the development of this theory. According to the theory, an exotic form of matter exerted gravitational repulsion for less than a millionth of a trillionth of a second following the Big Bang. Although we typically consider gravity to be attractive, Albert Einstein's theory of general relativity allows for the existence of a repulsive form of gravity. Under the conditions of the early universe, when temperatures were extremely high, Alan Guth asserts that the existence of this material was plausible. He stated, "It need only be a speck. When this speck begins to grow, the expansion is exponential." How did our universe begin, where is it going, and what caused it to exist in the first place are among the most intriguing scientific questions that arise when contemplating these fateful events and what followed. What existed before inflation began? The concept is that the universe is eternal. It has always existed, so there is no starting point to elucidate it. The laws of physics themselves appear incapable of distinguishing between the future and the past. The universe's entropy, or disorder, will increase as it evolves. The future is merely the direction of increasing entropy, the past is a state of decreasing entropy. The entropy will also begin to increase in that direction, if you follow this initial low entropy state backwards in time, towards what we previously referred to as the past. I believe that the individuals who lived along any arrow of time, including one that point backwards from our perspective, would not feel differently from us. Everyone will believe they are living from the past into the future, but what they consider the future will actually be the past. What can inflation tell us about the forces that hold together our universe? If only the visible matter existed in galaxies, there would not be enough gravity to hold galaxies together. With their current rate of rotation, they would simply disintegrate, or they would never have formed. Even at these high velocities, it is assumed that there must be other matter present, to produce a stronger gravitational field to hold the matter in place. That's dark matter. The physicists are calculating the production of primordial black holes, in a form of inflation known as hybrid inflation. Primordial black holes might be composed of dark matter. They may also be the progenitors of the supermassive black holes found at the nuclei of galaxies, black holes with millions or even billions of solar masses. Finding primordial black holes would be a monumental feat. Is our universe the only one? According to the theory of eternal inflation, once inflation begins, it never entirely ceases. But universes within universes continue to form, pocket universes continue to form. There is always a volume of exotic repulsive gravity material that can expand indefinitely, producing an infinite number of pocket universes in an unending procession. Each pocket universe will presumably expire, in the sense that it will run out of energy and cool down at some point. In the grand scheme of all pocket universes, however, life would not only continue eternally, but it would also expand exponentially every second. The problem with an infinite multiverse is that if you pose a simple question, such as what is the probability that a coin will land on its head if you toss it? The answer is normally 50%. In the context of the multiverse, however, the answer is that there are an infinite amount of heads and tails. Since there is no unambiguous way to compare infinities, there is no straightforward way to state that some types of events are common, and others are uncommon. This raises fundamental concerns regarding the definition of probability. Probability is crucial to physicists because our fundamental theory is quantum theory, which is based on probabilities. Therefore, we must understand their meaning. An important requirement is that inflation must persist long enough to generate the observable universe from a single, small Hubble volume. This is required for the universe to appear flat, homogeneous, and isotropic at the greatest scales observable. It is generally believed that this condition is met if the universe expanded by a factor of at least 10 to the power of 26 during inflation. Thank you for watching.